Hey everyone, welcome back to a Lit in Space Lightning Pod. This is Alessio, partner and CTO at Decibel, and I'm joined by my co-host Wix, founder of Small AI.
Hey, and today we are very happy to have Rishi Agarwal from GDM. What is your role at GDM?
A staff research scientist.
Staff research scientist.
And
occasionally you do these talks. It sounds like you do them internally, but then also you publish your slides. And it's like caught my eye on a few of them. And I think this most recent one, you said that you did a talk on distillation and it wasn't recorded. So I was like, why not let's jump on and talk about all this sort of post-training distillation for LLMs, because I think it's just the general field of post-training has just exploded this year.
Yeah, that's true. Cool.
Yeah, maybe you can give us a little bit of context on how or why this topic was relevant enough for you to do a presentation on it.
Yeah, so I guess that's a good question. I usually am an RL researcher generally, and distillation is something like a side quest I've done at Google. But this time around, I guess there has been a lot of progress. So if you think about distillation, I think what comes to mind is the 2015 paper from Jeff Hinton and others, which is the seminal work that people refer to. But then since then, it's been a decade, right? And there must be some progress that has happened since then. And especially now we're talking about LLMs. Back then we were talking about classifiers, which will let's train on ImageNet and what say. So I thought it would be a good idea to give a tutorial, at least internally at Google. And after the tutorial, what I did was I also published the part of the slides which were at least based on publicly available information. So I thought it'll be worth sharing. And that's it. And I think the reason is, so I mentioned I usually work as an RL researcher, and some of the new methods which are coming out are RL inspired, which look very different than what you typically think of when you think of distillation. So I thought that'll be a nice way to just talk about what people typically think of as distillation and what are the new latest kids on the block. And maybe some of them make sense, maybe not, but still worthwhile knowing what is possible.
Yeah, there's a purist definition, which is the Hinton definition. But I would say the current usage of the term distillation has kind of expanded a little bit.
Yeah, I think also how you do it, right? So usually, let's say the definition is very broad. It says we want to transfer knowledge from an expensive teacher model to a smaller model. And sometimes the model could be of the same sizes. But then, this is very broad. It doesn't say how do you transfer the knowledge. And usually people think that, we'll collect some data from the teacher and then we'll just fine-tune the student on that data. But that's one way of doing distillation. And there are other ways too, right? And I thought maybe we should talk about that. And I guess the motivation for distillation is kind of easy to grok. You would think bigger LLMs are usually better. And that was a trend a few years ago, even now. But in practice, what you care about is, let's say, the graph, which one of the hosts here created, which is the graph of cost versus performance. So you want something really good, but at a really good low cost. Even if something is really good, but it costs 1,000 times more than something else, maybe we still not use that because it's just too expensive for the use cases people care about. And then there are other use cases. Let's say you want to deploy a model in your smartphone. It's just not possible to fit a really, really large model there. So that's another challenge. And I think that's why maybe we still care about distillation per se.
Yeah, I think one thing I'll comment about this is I actually used to think about this as distillation as it's a fun way to to sort of fine tune a model or whatever. But now I really think about it as a deployment technique, in the sense that we're starting to get models that are too big to use in practice, right? The Llama 4 or 5Bs, even GPT 4.5 is too expensive. Nobody is really going to use it in any reasonable quantity. Claude 3.5 Opus, if it does exist, still not, the thing that we actually use is Sonnet, right? So it's almost like a deployment strategy. You train the large model, the teacher model, in order to distill. You don't actually expect to use the teacher model for inference anymore.
Yeah, I think it is really the marginal benefit versus cost argument, right? If the marginal benefit and capability is not worth the additional cost to you, then people don't want to use that bigger model. And it is very, very task dependent. Maybe you really want that capability, but sometimes, especially when you're doing things at bulk, maybe it's okay that you're slightly worse off, but it's much cheaper. And that's maybe one of the reasons, at least this graph, that's why you want to be at the Pareto frontier. And I think the other thing is the capability which we have right now, maybe next year it'll be much cheaper to have that same thing. And that likely is the result of distillation, right? It's not just because we are doing or figured out something magical. It is because distillation can help you bring the cost of any existing capability.
Yeah, it's a little bit of sawtooth, like you go up in capability, then you go down in efficiency, to make it more efficient and that kind of thing. The other thing I noticed as well, which I kind of pointed out, was the slope of the slope of the Pareto frontier is basically the state of the art of distillation, and the gentler the slope, the better distillation is. Which I thought is kind of cool.
Actually, that's a very good argument. Like, I didn't think of it that way. But
you see
right.
it improve over time, in the sense that it used to be this kind of very steep slope for intelligence, and now it's a lot gentler.
So you're saying basically we're getting better and better. At least this is costs. We don't know underlying what's going on, but you're getting better at serving the same intelligence at much cheaper, and the slope itself, saying the methods themselves might be improving. That's possible.
It's just like easing. Yeah. Okay.
Yeah, the other fun reason, which I think, if you go to this next slide, I think this is like one of the coolest reasons. And this is something that people have lots and lots of theories, and you can go to this thread. I think there's like hundreds of reasons people have given, but this is something that people have found again and again, that basically you can train a model on some data, or you can train a bigger model on that data and distill that model to another model, and that distilled model is better. Like this has been true. There's a lot of theories, some I know, and there's a lot more in this. You can see based on the popularity of this thread. And that's another reason that at the end, if you just want to train a good small model, maybe it's still better to train a bigger model. Like that's what you were mentioning earlier also, that maybe that's why we are training teacher models. But this kind of finding has still stayed relevant, I think. And at least I would say this is still true. And this is another good motivation for actually thinking about distillation.
Yeah. Is this really called dark knowledge, or what is this phenomenon?
So the dark knowledge actually is funny. If you go to the slides back, the dark knowledge comes from Jeff Hinton's slide themselves. Like he used to give talks about distillation where his slides were just titled dark knowledge. So,
okay. Interesting.
Those are also very fun slides to see from Jeff himself, like what's the motivation of all this thing.
And when you think about using this model for distillation, is there any changes you would make to how you approach RLHF and kind of preference tuning? You know, a lot of times the models kind of get narrowed down to be good for user facing things, but if you're just using them to then distill things, maybe you can skip some of that work.
Depends, right? For example, your distilled model could itself be RLHF, right? Maybe you want to skip the RLHF stage, let's say. So what if you have the final model you want to serve, and then you just distill it? Maybe you don't need to do anything else after distillation. So think of it as like what you want out of this. Let's say you say, oh no, I just want distillation so that I distill some base capabilities in my model, and then I will still do some sort of specific post-training afterwards. Then it makes sense to have a different teacher. So I think it depends on what you want out of distillation, because distillation is just saying, I can transfer capabilities from this teacher model to the student one, but that's not perfect, right? There's always some gap. So maybe you still want to self-improve that student, and that's what RL is for. So I would think maybe an optimal pipeline would look like you do distillation heavily, but then you still do some RL afterwards, because maybe there's still something you can get out of your reward functions or whatever your post-training stack is. At least in my thinking, unless your distillation gets you really, really close to the teacher, that at that point you'll be like, okay, there's no point doing anything more. Let's just do distillation and move on. That could happen, right? If a distillation was that good, so let's say you take like the best model out there and you can just distill it. And for the thing you care about, let's say if it's coding, and you distill it so well that on coding benchmarks and all the kind of coding tasks you're doing, it's just really nearly matching the teacher, then why would you do anything else afterwards? So it depends on how good distillation is. And that's more of an empirical thing, I would say.
Yeah. Cool. I can keep going. Section.
So I guess, so this is like the thing which was popularized by the original seminal paper, where we basically take the student, have the teacher, we run some input through it and get logits and match them. But this is not actually what is used in LLM. So maybe we can skip and go like a bunch of slides further. One thing I'll say is, so if you go up, it's just a bunch of math, but basically it's minimizing some sort of KL divergence or objective by matching the distribution of the student and teacher. Just keep that in mind. Like this is what the Hinton style distillation is doing, and it's using logits. It's basically, rather than the intuitive way to think about it is, it's doing next token prediction for LLMs, except you are using soft tokens. So if you go down a couple slides, I think that will come out. So the objective is the same, except rather than having a single hard token that you're saying, I want to predict this token next, I have soft labels that I have basically some probabilities for each of these tokens, and I'm predicting all of them together. So it's basically a generalized version of next token prediction, but at the end of the day, loss is exactly the same. The only thing changes is whether we have one hard labels, which is only one token gets a value of 1, everything else 0, or do we have soft labels? And this can, now you can see that this can be easily used for pre-training. And one notable example of this is Gemma 2. So Gemma 2 used distillation for pre-training, where they used logits or these soft labels, which is rather than having hard 0-1 tokens, which is I want to predict this next token, they have like soft labels for all possible tokens. And then they just run the next token prediction loss on this.
Is there an estimator of how much better? Because obviously you're just utilizing all the available information, right?
So this is like basically saying you observed some next token in the data and you assume that's ground truth. Here you're saying, oh, I'm actually relying on my teacher to tell me what is the possible next token after this sentence or this part of this, and then you assume that as ground truth, right? The objective is the same. The only thing is what information you assumed access to, and here we have more information because, well, I guess the teacher was trained on that human data, but we're hoping that it generalized. That's the dark knowledge bit, that maybe it actually knows more, that maybe there are multiple tokens which are possible. It's just that I only observed one of them in the data, but the teacher is telling me that, oh, there are these few tokens that are very likely after the sentence. So maybe I should be trying to predict all of these. And that is when maybe the magic of distillation is from. So you can see in these plots, right? If you can, so again, this is the kind of dark knowledge we're talking about, that, oh, if you train the student model from scratch, that's like always worse. So higher is like, I guess it's perplexity. So higher perplexity is worse. But similarly on the previous plot in terms of performance also, you can see from scratch is the top bar and distilled is the bottom bar. So there's no change. I have the same data and everything. The only thing is whether I'm just training this model from scratch or I'm distilling using a bigger model on that data. And you see that effect of, oh, distillation actually doing better. So that's the reason maybe people do distillation. It's just not cost savings. Maybe you're getting a better student model at the end of the day. You couldn't have just done it if you were to do scratch training for that.
Would there not be more quote unquote flops spent on training on the distilled model, because there's the flop spent on the teacher, then there's the flop spent on the student?
Yeah, that's actually a very good thing. I think there's definitely more compute. This is something I don't know if the Gemma 2 folks reported in the report. Was it compute matched or was it data matched? But that's a very good comparison. Like you should be ideally comparing on compute, like whether if you do more trained updates on the same data, which matches, let's say the amount of compute you used. Okay, so this is actually the kind of distillation which is very, very common, right? Which is, this is like the one we commonly use for LLMs. We call it distillation using synthetic data. It was actually introduced back in 2016 from this paper, the sequence level knowledge distillation. But what they do is they have some prompts. You just take your teacher model, generate some outputs, and then you just do supervised fine tuning on this data. That's like the simplest thing possible you can do. And it is also a very common method. The nice thing about this method is it only needs API access, right? Like, so you can take any model out there and you can just prompt that model and generate outputs using that. And then you can just use that data. Now, this was also in the news recently, if you were following it. The nice thing is, like, I guess if you go down, next slide, this is exactly the same loss that we were optimizing earlier with the principal distillation, like the KL divergence. It's just a different way of doing it. So it is a very principal objective. It is minimizing some sort of divergence or KL divergence between my teacher distribution queue and the student. And it's just a different way of doing it, where I am just basically sampling something from the teacher and fine-tuning the student on this. So the simple thing which people do is very principled and is optimizing the same loss. It's just assuming access to different kind of information. So here we don't assume access to any sort of logits or next token probability distributions. Here we are just sampling from a teacher, and that's the only access we assume. And then we just fine-tune the student on that data. So same loss, different way of optimizing it. And it just turns out to be simpler. So that's why everyone uses it, right?
Yeah.
And I guess a better version of this is you can do something like best of n, which is, let's say this was something which was used in DeepSeek. So if you saw that paper, they trained the DeepSeek reasoner model and then they distilled basically that model to other models. What they did was they took the best model they had, they generated a bunch of samples, they filtered them based on correctness, because these were on tasks like coding, mathematical problem solving, and a bunch of those things. So they saw what are the outputs which actually get the right answer, or they get past the test cases or whatnot. They pick those and then they just fine tune the model on that data. So if you go down, I think that's what the results from DeepSeek. Yeah. So you can see these are taken from the DeepSeek report itself, and people can read that for more details. The one nice thing about this kind of distillation is it doesn't matter if you have a vocabulary mismatch, because we're not using the next token distribution or probability labels. You can distill from one model which uses some random tokenizer to another model. That's like a very good feature. Like that's the cool thing about. That's why they were able to distill from DeepSeek model to Llama or Quen, and you don't have to even think about that tokenizer. And that's why this is common, right? Like it's very easy to do. You can just need an API and just collect data, fine tune that on that data, the student model, and that's it done. And
But
you can already get pretty close.
it's still a lot less efficient than the logic matching distillation, right?
It depends. I guess that's a complicated question. It depends on the thing. But yeah, logits are definitely assuming access to more information. So it can be, but then again, you don't have access to logits if you want to distill, let's say, a black box model. So, but then again, it's not legal, I guess, to distill a black box model, or at least the terms of conditions don't allow you to do that. But for open models, yeah, you can do better because you have access to logits. So why not use them? At least that's my take. So, and I guess this, maybe we can skip, but this is just saying when you're doing best of n, why not keep the top k rather than just the top? Because if you're already generating, let's say, a lot of samples, why throw away, let's say if you have some sort of scoring mechanism of how good something is, and this thing is called MBR in the translation literature. But anyways, this is another way of best of n. So the key idea is very simple. Just like use some of just don't throw away everything. Just use the top k samples rather than just the top one. And this might be better, and that's true. So that's like a simple thing worth trying if people are doing synthetic data distillation. I think I'll maybe, so there's small gains you can see. If MBR is, let's say, using just the top one, and then if you increase from 5, 10, like top 10, top 20, top 40, you can see slight gains as you use more samples. I think the one below is much more interesting, and this got a lot of popularity on Twitter, and funnily enough, every few months, this keeps getting retweeted and getting viral. But maybe I'll clarify what's going on here. But basically, the simple idea here is just that if you have two models, right, there is a sampling cost you're paying. So you can generate data from a really big model, or you can generate data from a smaller model, but you can generate a lot more of it because both of that use the same compute. Because the sampling cost, or flops, is proportional to the number of parameters in the model times the number of inference tokens. And there are some assumptions here, and I'm assuming we are using KV cache, but assume this mental model that the cost is proportional to number of parameters times the number of tokens. And for a fixed number of tokens, if you have a much smaller model, so let's say Llama 70B versus Llama 7B, you can generate 10 times more data in principle, right? So now you can ask this question, well, is it actually better to generate data from Llama 70B, or is it better to just generate a lot more data from Llama 7B and assume we can do something like best of n, which is we have access to some sort of filtering function or reward function? Then it becomes even more interesting, right? Because now you can filter this data too. So if you go down, so one thing we found consistently, so here we had two models, Gemma 9B and Gemma 27B, and we found consistently that actually generating data from 9B in a compute match setting is always better, even better for distilling or actually improving the 27B model itself. So which is we are fine-tuning the bigger 27B model. There are two things we can do. We can generate data from the 27B model and filter that and fine-tune it. So that's self-improvement using some sort of reward function. Or we can generate data from the smaller 9B model. It's just that we can generate a lot more of it and fine-tune the 27B. We found that actually that's better to do.
Wow.
So this is, again, the magic is because we can generate a lot more samples and we have a way to actually select what is a good sample because we are doing this on domains like reasoning, like math coding, so we can filter that. So if you go down to the slide,
quality,
if you do cost match, so I was talking about compute match, but if you think about API pricing, like let's say we have two models, Gemini Pro and Gemini Flash, the pricing of Flash is 35 times cheaper than Pro. And now actually it's even better to generate data from the Flash for the trade-off you get, because you can generate 35 times more data for the same cost. Let's say if you have some dollar budget of $100, you can generate samples from these two models. And it turns out that actually just generating a lot more data from Flash and filtering that would be much better. These are all results on some math reasoning benchmarks. I think it's Hendrik's math.
Yeah, I mean, the intuition is really that you're injecting more data through the filtering process, right?
Yes. So it's not just more data. It's more data, but also going through this filtering. If you just do more data, well, again, you have a weaker model, right? So more data from a weaker model cannot just be better than less data from a stronger model. Maybe true, but that's unclear. But because of the filtering function, which means for domains like reasoning, this could actually very well work. So that's another reason to use a small model. Okay, now I think this is going to be switching gears. So this is what I was talking earlier, that RL-inspired distillation. So if you think about distillations, or generally just next token prediction, there is a mismatch at training time and test time, or inference time, which is at training time, we are basically training on a fixed data set of outputs, which is I already give you the output and you fine tune on that. Let's say that's what that was being done in the synthetic data distillation. I already gave you some input and output and you just supervise fine tune on that data. But at test time, the student itself, or the student model itself, is generating tokens one by one, autoregressively. This is also the same difference which happens in SFT versus RLHF. In SFT, you're teaching it to copy something. In RLHF, it is learning what to do using a reward function. So there's a big difference. And there is a mismatch, basically, at training time and inference time. And just imagine the autoregressive nature of models and what we are doing at training versus what happens at test time.
It's called exposure bias.
This is like something, this is like another term for this mismatch, but there's a bunch of papers you can find. But yeah, this is also known as that in the NLP community. But really all that there is to it is this thing is train-inference mismatch, right? And then I guess really like think about it this way. This is like also very well known. This inference mismatch is very common in the RL community. It's like this work is done back in so when people are trying to copy agents, which might be relevant now again, you can do behavior cloning or supervised fine-tuning, which is very common, but the RL folks figured out a much better way. They call it Dagger. I'll explain what that is very quickly, but just imagine what's going on. So let's say you're training a student model on some fixed data distribution. Now at test time, the student model makes a mistake. So here, let's say the student is learning how to drive a car, and all the student was trained on how the teacher learns or how the teacher is driving the car, right? But there are scenarios which the teacher would never do because the teacher is a good driver. So maybe he'll never run into really bad situations, but the student might run into such situations. Let's say I see some tree and I'm going to crash into that, right? The teacher is never going to show you such a scenario because it's generally teacher is a good driver. And if you collect data from that teacher, they'll just show you what does good driving looks like. Yeah. But that means that you cannot recover from these things. Like if the student is going to like crash into something, it has not seen this kind of data before. And this is the mismatch I was talking about, that it hasn't seen, if I made this kind of mistake, what do I do? And I guess pictorially, if you see the left picture here, that you can see the learner is falling off the cliff and the teacher just never goes there. Like it's just like, this is like from Looney Tunes, it's adapted from someone else's slide. But this is like a common problem that also happens in RL or any sort of agentic tasks. So this is like the de facto approach people use when they are distilling in self-driving style situations or other agentic situations. And this is a method from 2010 or something, I think. But this was designed for RL agents. And we thought, well, we can close our eyes and think of LLMs as agents. And eventually LLMs will become agents, but LLMs are also producing token by token, right? And maybe they are, think of these as actions, so they are doing things. And then we want feedback on, is this good enough or not? So you can assume the similar methodology can be applied. So if you go down, what's the fix? The fix is very simple. The main change is, rather than sampling the output sequences from the teacher, we just sample that from basically the student itself. The student is sampling these tokens or sequence of words or text or whatever you can think of that as. Now, we run inference using the teacher on these tokens. And this can be parallelized because once you sample the sequence from the student, you can just send the entire sequence to the teacher.
Yeah.
Yeah. And then you can get logits for all of this. This is just running inference, right? So this is not autoregressive. You just send it in parallel and you get logits. And then you minimize the logits. So the only main difference is you're sampling data from the student rather than teacher. And what it looks like is basically at every point in time, I'm asking the teacher that, hey, what do you think about this? Do you think, is this good enough? Like, would you have done this or would you have done something else? So at every point in time, the student is asking teacher for feedback. And the feedback is the teacher is going like, I will not do this. I'll do this instead. And the student is like, okay, I guess I'll keep that in mind. But it's getting this kind of correction feedback. So imagine the scenario I was saying earlier that, if you run into a scenario where basically you're really close to colliding to a tree or something, the teacher would say, actually do this thing so that you avoid this collision. Or it will, before it's actually even going to the collision, teacher would be like, I'll never do this kind of thing. Do something else. So this is like something, and if you go up, it seems, I guess this is like pictorially. The nice thing is this, basically there's no train test mismatch. The way we are generating the data is also the same thing done at test time, which is at training time, the student is generating the data autoregressively. At test time, the student is again generating the data autoregressively. So there is no train test mismatch of that sort. And that's like the main kind of fix this kind of on policy thing approaches. Now, I'll maybe mention one interesting detail afterwards. But if you go down the slides, I guess it's pictorially mentioning what's going on. So we sample data, we get logits, we minimize some sort of loss. If you go one more slide down. So the nice thing is you can derive this actually. So all you need to do, at least in math, if you just flip the direction of your KL divergence. So earlier we were minimizing KL between a teacher and student model. If we just swap that order, because KL is not symmetric, you will actually get this kind of distillation.
Oh, that's cool.
So it's like, that's like nice, cute math you can write to say, oh, actually I can derive this and this is very principled. It's not a hack. The other nice thing is you don't have to do full RL. Basically, you can sample from the student. And I said, oh, you just optimize some loss. You don't have to backprop through the sampling distribution because that also depends on student parameters. That becomes full RL. And there's another paper on that. But basically, if you still want to do supervised training and you're only changing which data distribution you care about, and we are saying we care about the data distribution which student samples, because that's what we anyways want to use at this time. So that's the other trick which people have done in the literature of RL literature. And we're saying, well, what if we just do that again with language models? So this is a paper we wrote in 2024, but basically it's saying there's a way of doing distillation which RL people use all the time. What if we try that for language models? And that works pretty well. So if you go to the next slide, you can see the results. And it also answered the question. So this was done on very small scale tasks, right? These are like very specific tasks like summarization, translation, or reasoning with chain of thought. The supervised fine-tuning or red line is the synthetic data distillation we were discussing earlier. So that's synthetic data, not synthetic data. It's distillation on human written outputs. GKD, if you look at the light sky blue line, that's synthetic data distillation, which is if I just take the teacher model and just generate data from that and distill. Supervised KD is using logits, and this green guy is basically sampling from the students and using logits.
Yeah.
But you can see, I guess one cool thing you'll see is it's not always the case that synthetic data distillation it's worse than logits. Like sometimes logits can be worse off. So if you look at the T5 base 250 million scenario on GSM 8K, on the last plot, you can see that synthetic data distillation can actually be better than using logits. Right? Okay. So that can also happen. Like it's basically... But usually I would say if you have access to logits, it's probably worth using them. And the green curve, which is doing on-policy data, is using logits anyway. So that does have the efficiency argument. So this kind of thing was used in Gemma 2 post-training. It's mentioned briefly, like there's no details there, but it was used there.
Excellent.
But there's no way to know ahead of time. Like you don't know ahead of time based on the task whether or not distillation logits are going to be better. You just got to do it.
I would generally say I think if you have more information, usually it's probably better to use it. It might be a capacity thing, right? Like look at the T5 base model. How many parameters are 250 million? That's not even a language model at this point, we consider. Like that's like micro size because people call 0.5 billion tiny. And this was a base model back in the day. So I would say it depends heavily on the capacity to some extent. My opinion still is if you can use logits and it's not too inconvenient, probably worth it. Maybe your method is not as good. And again, the method which we are competing against is like a method developed in 2015, right? Like the logit distillation thingy, the supervised KDs, and better methods like the green one can easily make logits much more useful. So I would say that's maybe the blocker with logits. And more research would be really helpful there. Anyways, so I would say my answer is use logits if you have them.
Yeah.
The other fun thing, and I think this is a very nice plot. This is worth internalizing actually. So there is this notion of, how do I say this? So when let's say you're doing distillation, there's always a model capacity mismatch that the student model is generally much smaller than the teacher model, right? And now actually it depends on which direction of KL you optimize. It changes what the student would learn. So here it's a very idealized scenario where I have a bimodal Gaussian distribution. That's your purple guy. And then the green curve is the student model. It's a unimodal Gaussian, which means I can only fit one of the peaks, right? And now, depending on which direction of KL I optimize, I have very different behavior. So these are called mode covering and mode seeking KL. Typically what we use is with this mode covering KL, the one on the left, that is the standard distillation loss that everyone uses. But you can see the behavior. And you can already see what's weird about it. It's putting a lot of mass on places where there's no mass put by the teacher. Like the teacher would not sample anything in that regime where the peak of the green curve is. But that is exactly the behavior you're getting when you optimize for this direction of KL. While if you look at the other guy, you can see that what it's doing is it's covering one of the peaks, but it's basically putting no mass altogether on other parts of the distribution. So this is called mode seeking. So that is basically the difference in these two directions. And supervised KD minimizes the direction of KL between teacher and student. That's similar to the one on the left, while on-policy distillation minimizes the other direction. So you can see the behaviors. It's basically saying I'm happy fitting one of the modes, or I'm happy basically getting one way of getting this capability right, rather than getting all these different ways of getting the capability right. So if capacity is a constraint, then you can see the behavior, or at least why there is basically the difference in divergence use.
Yeah, I would say this is like a very exaggerated example. Obviously, most actual text distribution doesn't look like that.
Yeah, also this is Gaussians, right? This is like saying if world was perfect and pictures look like Gaussian. So if you go down, actually that's good. You mentioned it's, so in practice, this is what things look like. You get a trade-off. There's a trade-off between diversity and performance. So on the y-axis, I'm showing performance. On the x-axis, I'm showing similarity, or basically how, like 1 minus diversity. So more similar things are less diverse. And you can see depending on the KL, the divergence you use, you get like a trade-off. So if you use the one direction of KL, you get like pretty high diversity or low similarity, but low performance. On the other end, you have high performance, but low diversity or high similarity. So if you look at just like one of the curves, as you go along the x-axis, you're actually losing diversity because things are getting more and more similar. Mm-hmm. So there is that trade-off you're facing. And now for any task you care about, I would say like basically you'll have the sign of trade-off. The general recommendation I would give people is that maybe use a mixture of half and half. Like that's what some people have used, right? That's like saying, basically saying, I don't know what I want. I just want something to work well enough. I'll just do half and half and hope that it works out. And generally it would, I think. So there are different ways of mixing half and half. This is one way. JSD, the Jensen-Shannon divergence, is another. But this is just like our way to say, I don't know what I want. Let me just like do this and hope it works. And usually it does. Okay. Now the most fun slide. I think I really like this slide. There are 3 easy steps to implement this distillation. You go to an RLHF framework. Oh, I think my AirPods died. Can you hear me still?
Yeah, I can hear you still.
Yeah, okay, that's good. So there are basically 3 easy steps to do this thing. First step is you go to an RLHF, RLXF, whatever framework you have. You turn off the reward term. So you delete the reward part of it. All you're left is some KL term. And now you swap your KL, the anchor policy, to a bigger teacher policy. And there you go. You have implemented the distillation we are talking about. So RLHF or RLXF is already doing 2 things. It's doing reward maximization subject to some KL constraint. The KL constraint is usually to the same policy as the student or some SFT policy, but it doesn't have to be. It could be a bigger model. And yeah, basically that's it. So that's like the cool thing that.
I mean, it's very interesting. Why are we turning off reward maximization about KL divergence minimization, right? Like, why is this so profound to you?
Sorry. So saying we are basically just interested in distillation.
Why is this so profound to you?
I'm just saying the reason it's interesting is because I'm banking on any existing RL framework. This is how the Hugging Face people implemented this. But I'm saying that usually infra is a big bottleneck for these kind of approaches. But what I'm trying to say is that the infra already exists. All you have to do is delete a bunch of pieces in that infra and you're good to go. And I guess that's why it's already, you also asked a good question. Why do you have to turn the reward term? You don't. That's the next slide. You can actually combine RLHF and distillation together because now you're doing 2 things at the same time. Basically, I'm saying you already get this free infra for free. Like you have it. You just have to make sure that you can fit in their teacher model there in that infra. And that's the main change you have to do. And you already have implemented this sort of distillation because we are anyways sampling from the student when we are running RL. The main difference is rather than using some logits from a teacher, we are usually maximizing rewards and logits are coming from the SFT policy. While here we're saying, well, I actually want to use a bigger model as my teacher and do this.
Okay. Nice modification.
Yeah, I think the rest of the slides is just some application. I'll actually, can you skip this one? I think I'll go for one more. Yeah, this one we can skip. I think there's a more fun application, which is much more relevant for people. So if you go down, next slide. Yeah, if you go further.
I think the share might.
No. My computer's acting up a little bit.
Okay, this one.
Decoding.
Yeah, so speculative decoding, I think I'm assuming people know about it, but basically the way to understand it, we have a smaller model which is proposing some tokens and the bigger model is accepting those tokens. So you can propose multiple tokens at a time, and this bigger model can say, I like them. Let's just go with that. And basically, you do not change this distribution or samples from the bigger model, but you can make it much faster. Because now, rather than producing token one by one, you can produce a bunch of tokens at the same time, because you can use the small model to produce those, which is cheaper, and then the bigger model can just accept those. Anyways, read about it. It's very cool as a technique. Now, the thing is, the effectiveness of this method depends on how close the sampler, the small model is to the bigger model that we want to speed up. And actually, distillation exactly fixes that, which is by distillation, you can make things closer to each other. And we found that actually, if you do that, you can make speculative decoding faster, which means you distill. So your student, you have a better student model, but then you can also speed up your teacher model using this distilled student with speculative decoding. So you get two things for free.
So every large model should always have
something for
every large model should always have a student model for.
Yeah, basically, even if, let's say, you don't care about the student, the large model itself would benefit from having someone close enough to itself so that we can speed up serving of that large model. And this was actually used. So I guess the cool application of this I can mention is the next slide, which is AI overviews at Google. I don't know if people have seen this or this kind of thing. Like there is this thing that comes up, and that actually uses this technique of speculative decoding. But then you can all obviously imagine that, they have some small model, which is still from the big one, which makes this even faster. Oh, actually, last slide. I think this is like hot off the press, I guess. So now you can merge all the ideas we have discussed so far. This is like this paper at iClear this year, but basically we're saying, well, we are sampling from the student, and then we're getting feedback from the teacher. But then there are scenarios where maybe the student just does something really terrible. The teacher is like, come on, man. Like, I can't tell you anything here. Like, this is just too bad. I don't know what to do. And that's exactly what this is for. This is saying, basically, you get inspiration from speculative decoding. So the student is sampling, but is making sure that the teacher is like, yeah, okay, this is reasonable. If something is too far off, the teacher will take over, and the teacher will say, okay, I don't think this should be sampled. I would sample one token from the teacher and then continue with the student. So basically, it's like, imagine the driving scenario again. It's basically saying the teacher is like, I'm never going to crash, but okay, you are in this situation. Let me actually fix this trajectory and let's continue rather than you crashing, because after that point, I cannot give you any meaningful feedback. So it's much more expensive because now your sampling involves speculative sampling itself. So now you're interleaving sampling with the student and teacher. So the infra for this is even more complex, but you can see that this is more efficient. So if you go down, I guess that's the
Yeah. So like the comp is hidden in the actual inference. Yes.
If you go to the last slide, I think that's the most interesting one in the current context. So this, I think, is maybe the main trade-offs when you're thinking about what distillation to use. So let's say if you're thinking of offline distillation, and I guess I mentioned soft, but it could, soft meaning you're using logits or next token probability distributions or not. One thing is, when you're doing online distillation, you don't need to have any sort of annotations. You don't need to save these to disk. You can just like press a button and basically it'll happen because you assume access to a teacher available online. But then that ends up being more compute expensive because you're running a student, but you're also having access to a live teacher for running inference on that teacher during training itself, which is obviously more expensive. You're also not relying on just offline data. You're sampling from the student, same as RL. Like you are running samples from that student and it's on policy, which is you're always sampling from your current model. So that is going to be more expensive. That said, there are nice things about this, which is it manages a strain test mismatch. The other thing is in the RL literature, there are like results which show that actually this kind of distillation is much more optimal for agentic tasks or really long horizon tasks. Think about like when you're outputting hundreds of thousands of tokens. If you're, let's say, doing that, it's very easy to imagine that there might be some places you'll make mistakes if you only learn from offline data. And basically, you need this sort of online sampling to fix that. Now, this is TBD, whether how far we can go without it. But at least there are already a lot of results in the deep RL literature, not work on LLMs, but other tasks, where they show that, okay, if you do just offline distillation, that's going to be much more suboptimal than doing this on-policy distillation thing. So these are like some of the trade-offs you will face when picking on what distillation method to use. And I think sorry.
Oh, sorry. I think that was an echo.
Okay. Yeah, I think this is maybe one of the most important things to consider when people are thinking about distillation, because they have to make some of these decisions. Like, what do they have? Do they care about, let's say, trying things and training quite quickly, or do they want a process where they just have to do this once and that's it? They never have to come back to it again. So based on that, trade-offs are very different. And also, I guess, more recently, when you're thinking about agentic tasks or long horizon tasks, that's where maybe things get even more interesting, because maybe it looks very different from what distillation has been done for, let's say, small, let's say, few tokens, thousands of tokens kind of tasks versus hundreds of thousands of tokens tasks. Those, I think, might have very different behavior.
Cool. Let me on the screen share. That was really comprehensive. Actually, I didn't realize this was accepted for ICLR 2025. So it sounds like you'll be presenting this in Singapore.
I think it's basically, I told you about the frontier already. So people can now go and think about this and be like, well, this looks still dumb. Can I do better? And I think that's generally a good mindset. And also, well, I know about this now. Maybe I can try it. Because I think a lot of people don't know about some of these new things, partly because they're very new and partly because they have not propagated that widely. But it's easy enough to try that it's worth trying, given the fact that it's so closely tied to the RL infrastructure people have these days. Or at least that's my feeling.
I would say one challenge I have, and maybe we can kind of close it off from there, is that live teacher kind of defeats the purpose.
Not really. It depends on how valuable the task is. Like, I guess it's a question of, would a 10% jump in capability, because I think this is something someone told me and I kind of internalized it. They said, you distill a model once, but you serve it billions of times. And I think I realized that, okay, what they're trying to say is it's worth spending the additional compute now, because if this model is the model which you're going to just serve to like lots and lots of people, maybe it's worth the extra capability improvement. But then again, it really depends on how much capability is the threshold. Because I would say try the simplest thing first, which is synthetic data distillation. That already gets you to 80% of the job or 90% of the job. And now the question to ask is this good enough? Or do we want to do more? And I think that's where you decide whether you want to do this more complex distillation things which have this infra needs. My answer is oftentimes we do, because I guess if we can push that Pareto frontier really up, right? And be like, oh, we can serve you really, really good capabilities, but at a really cheap cost. That's how maybe these newer, better distillation methods can come into the picture. And again, hopefully it's only done once, like you're not doing it again and again. So the point is, it depends on how valuable this model is, and with like making this model twice as better, but with the same cost, is that meaningful enough and worth the additional complexity? Or at least that's my answer. So I would say always try the simple thing first and then decide whether it's worthwhile doing the more complicated thing. Sometimes it is, sometimes it's not. And yeah.
Any thoughts? Reasoning, distillation?
Yeah, so I would say that's what I was trying to allude to earlier, that I guess synthetic distillation would get pretty far, and people are mostly working on that. But my hunch is that the logic-based distillation can go even further, and you might be able to even close the gap with the biggest of the teachers you have. Because I don't think you need a huge number of parameters, because the reasoning process is very, very, like it's basically a really long sequence, right, at the end of the day. And the model is producing these thoughts. And to reason really well, maybe it's not about capacity, it's about using this inference time compute. Well, my hunch is like synthetic data distillation would go very far, but a better distillation method can maybe even start getting to close the gap. And you might have a very strong small reasoner. And that will be like a big uplift. People are not trying it because, again, we don't have access to logics. It's annoying to use let's say if you're trying to distill from DeepSeek, you can't serve that huge model and have like a live teacher running because it is going to be expensive. But then again, maybe some people can afford to do that, and it's worth trying to push that and see if we can push much further. Because the results I showed you earlier, basically on math tasks, we're able to close the gap reasonably well. On coding, there was a huge gap still after synthetic data distillation. Now, how do you bridge that gap? There are easy ways. Either you collect a lot more data, a lot more prompts. That's obviously a simple way to get about it. Or you try to use your existing data and annotate this with logics. Now we're at supervised distillation. Or you go the extra mile and be like, let me just generate data from my student and ask my teacher model to see what happens. And I don't know the answer, but I feel like that is where it depends on how good of a student you want. That will dictate what kind of distillation method you use. Likely for most people, maybe the simple method suffices. But then I'm guessing for the like, let's say you want your model to be much better than others, and that is maybe the winning edge you have, then it's worthwhile pushing for that extra, because it's one-time complexity cost, I feel like, and we already are paying that when we are doing RL. So it's not that big of a cost, honestly.
Cool. Any call to action to wrap up? Obviously, you're going to be clear. We're going to be there too.
Yeah, call to action is mostly like assume things are suboptimal and we can do better. I think that's maybe my call to action in anything. Think about what method we are using and how old that is. And very likely you'll find that, we have been using this kind of okay thing. It's simple. That's why everyone's using it, but it's not really good. And usually that helps you. Even if you are like doing something really good, you might end up finding something better. And I think that's a good hunch for people. Even when you're doing practical things, like just don't get satisfied easily. Like just ask these questions of why am I happy with this? And can I do better? And usually if you start asking these questions, I think you move further along. And the other thing is, I think use some of the tools we have to actually discover these. Like I think one problem I have in the AI is there's too many things going on, a lot of cool stuff. It's very hard to find the cool stuff. And a lot gets lost in this. And I think even finding some of these cool stuff is going to be very important in the coming years to connect the dots and maybe try out the relevant things. So I guess maybe I'm saying I saw the deep research style podcast, but yeah, use those kind of tools a lot, and maybe that will help you make the connections you need. Still have to do a lot of your own thinking, but like finding some of these things is like, for example, the kind of things I presented were mostly saying people used to do this thing in RL this way. We are doing LLMs now, but we are not using any of the things RL people used to do. What if we just do that? That's it. And suddenly you have a much better method. So that I think kind of helps, especially when we are again talking about things like agents and reasoning and whatnot. I think a lot of the things are probably done on a small scale in the RL literature, in games and whatnot. And a lot of those ideas would be relevant again now. It's just worth thinking about which ones, and I guess both in practice and also for research.
Awesome. Yeah, thank you for the time. That's great.
Yeah, cool. All right. Thanks for having me. It was really great.